Sudoku solver using backtracking. Welcome to this video on solving Sudoku puzzle using AI techniques, specifically the backtracking algorithm. Today, we will explore how artificial intelligence can enhance the process of solving Sudoku puzzle efficiently. Sudoku is a logic-based puzzle that requires filling a 9x9 grid with numbers. The goal is to complete the grid so that every row, column, and 3x3 subgrid contains all the digits from 1 to 9. In this video, we will dive into an AI-driven approach to solve Sudoku puzzles using backtracking, a popular algorithm used in constraint satisfaction problems. Backtracking is a systematic method for solving problems by attempting partial solutions and eliminating those that don't meet the required constraints. For Sudoku, this involves filling numbers in the empty cells of grid. If a conflict arises, we backtrack to the previous step and try a different number. This recursive approach allows us to efficiently navigate through the grid. By integrating artificial intelligence with backtracking, we can enhance the process even further. AI techniques analyze patterns in Sudoku puzzles, predict potential placements, and optimize the search process. This makes the backtracking approach faster and more efficient compared to the traditional methods. Let's break down the backtracking algorithm for solving Sudoku. Find an empty cell. Try placing numbers from 1 to 9 in the cell. Check whether the number placement is valid according to Sudoku's rules. If valid, place the number in the cells. Recursively attempt to solve the next cell. If any conflict arises, backtrack to the previous cell and try a different number. This process repeats until the grid is fully solved. The first step in implementing the backtracking algorithm is reading and displaying the Sudoku grid. The input function reads the initial puzzle, typically a 9x9 grid with some cells pre-filled and others left empty, represented as zeros. The print function is responsible for displaying the final solved grid in a clear format. Here, print board is the function that will display the Sudoku. This function will loop through the rows of grid and print the solved Sudoku in a readable format. The heart of the algorithm lies in the backtracking function. This function attempts to solve the puzzle by filling the numbers one by one, checking if they fit in the Sudoku's rules. Here's how the backtracking function is structured. In this function, find underscore empty locates the next empty cell. If no cells are left empty, the puzzle is solved and function returns true. If there are empty cells, the function tries placing numbers from 1 to 9 in the cell. For each number, it calls a function isValid to check whether the placing number violates Sudoku rules for row, column, or subgrids. If the placement is valid, the number is inserted and the function recursively solves the next cell. If the placement leads to conflict later, the algorithm backtracks by resetting the cell to 0 and trying the next number. The isSafe function ensures that a number placement is safe according to Sudoku rules. It checks three constraints. The number doesn't appear in the current row, the number doesn't appear in the current column, and the number doesn't appear in the 3x3 subgrid. This function loops through the rows, columns, and subgrid to verify whether the number already exists. If any rule is violated, it returns false. Otherwise, it returns true, allowing the number to be placed in the grid. Let's see how the algorithm works with a sample input and output. A Sudoku puzzle grid where some cells are filled and others are empty. The algorithm will fill the empty cells by trying numbers, backtracking when necessary, and displaying the completed puzzle. To enhance the performance of the backtracking algorithm, we can apply several optimization techniques. Constraint propagation: reduce the search space by eliminating impossible number placements earlier in the process. Heuristic: prioritize certain moves, such as filling cells with fewer possible candidates first. This reduces the number of backtracking steps needed. These strategies make solving even difficult puzzles faster and more efficient. The principles of solving Sudoku using backtracking and AI are not limited just to puzzles. They can be applied to various domains, including puzzle generation, game development, and even resource allocation problems. Understanding these techniques can lead to innovation solutions in a variety of fields. Despite its effectiveness, the backtracking approach has its challenges. For extremely difficult Sudoku puzzles, the computational demands can be high. Efficient data structures are needed to manage the grid state, especially as the complexity of the puzzle increases. Addressing these challenges is crucial for practical implementation. In conclusion, the AI-driven backtracking approach offers a powerful method for solving Sudoku puzzles efficiently. By leveraging AI techniques and optimizing the backtracking process, even the most complex puzzles can be tackled efficiently. This showcases the potential of artificial intelligence in problem solving and opens the door to further applications in other areas.